Hi, I'm Laren, and this is Knife Steel Nerds. And on screen is me from a few weeks ago pouring Costco canola oil into a bucket. Why canola oil? Well, for one thing, it's the most common oil for knife makers to use when they're trying to cheap out. They want a cheap oil so they don't have to pay too much to make some knives. Some will use motor oil, but when I looked up a paper comparing motor oil and canola oil, the motor oil was much less effective. So let's just use the canola. I also bought a whole bunch of commercially available oils so that we can compare with those and see how they do compared with canola.
These are my oils.
One way that the speed of oils is compared is with the nickel ball test. They take a 12 millimeter nickel ball, they heat it up to 1,620 degrees, and then they quench it in 200 milliliters of oil or whatever the quenchant is. When they heat it up hot, it's non-magnetic, but when they quench it back down, it becomes magnetic again at about 670 degrees. So when it becomes magnetic, it is attracted to the magnet at the side of that beaker there. When it reaches the Curie point where it becomes magnetic, it's attracted to the magnet, and they stop the test. And the amount of time that it takes is how we rate it in the nickel ball test. So 2 seconds for water is extremely fast to cool down the nickel ball. If we quench in a fast oil, it can take like 7 to 10 seconds. For a medium oil, something like 11 to 14 seconds. And for a slower normal oil, it's just much longer than that. So this is how we rate our different oils or quenchants. So I bought a bunch of different oils. I also quenched in water for this study. One I bought is Parks 50. It's probably the most common used by knife makers in the fast oil category. It takes about 7 to 9 seconds to cool the nickel ball. Parks AAA is a little bit slower. It's sometimes called a medium fast oil. Quench Fast is sold by McMaster Carr as an 11-second oil. I couldn't get more information on what its range might be for the nickel ball test. Quenchel 521 is a medium to slow speed oil. And Quenchall is the 28-second oil that McMaster Carr sells. So it's a very slow oil. And we'll also be able to find out, where does canola fit in all of this? Is it super slow or is it pretty fast? So that was one of the big questions going into this study, is just how fast is canola and how would it do in a nickel ball test? I did some searching through the literature on nickel ball results on canola. I found nothing. Some studies did look at canola, but never for the nickel ball test. I think the reason is that the nickel ball test is just outdated at this point. More commonly, they'll do what's called the Inconel probe test instead. The problem with the nickel ball test is it's just a single measurement, just the time it takes for the nickel ball to go from high temperature down to the Curie point. But we want more information than that because there are different stages to cooling, and we don't know where the oil is reaching its maximum cooling rate, where it's slower, how fast is it at high temperature, how fast is it at low temperature. So the Inconel probe test allows us to see these things. So instead, the Inconel probe is also a thermocouple, so it's measuring how fast the Inconel probe cools while it's in the oil. Otherwise, the test is relatively similar to the nickel ball test. Then we can take the instantaneous cooling rate at each position along the curve, and then we get another curve that looks something like this, which is our instantaneous cooling rate at each temperature. And this makes it a little bit easier to identify the different stages in our cooling behavior. So the first stage is vapor blanket formation. When you first quench steel, or in this case the Inconel probe, we instantly vaporize the surrounding oil or water, and it forms a insulating blanket around the steel, and this makes the cooling rate somewhat slower. Then the vapor blanket breaks and we start to get boiling off of the probe or the steel, and then that is our maximum cooling rate. Finally, when it has cooled down enough, then we get slow cooling through convection at the end. And so normally we use these cooling rate curves to compare different oils. So on here I have a 7 to 9 second, an 8 to 10 second, a 10 to 12 second, and a 15 to 22 second oil. You can see that the behavior is roughly similar between those three fastest oils from 7 to 9 up to 10 to 12. It's just they get slower and do not quench steel as rapidly. The 15 to 22 second slower normal oil does behave a little bit differently. Its vapor jacket lasts until a lower temperature, and it's a little bit harder to break up that vapor jacket, so it's a slower oil. Canola behaves a little bit differently. It doesn't usually form a vapor jacket, and so its peak cooling rate is at a higher temperature than normal commercially available quenching oils. However, it starts to slow down at higher temperatures when compared with the commercial oils. And this is going to be important, as we'll see later on. Water, however, is much faster, just like in the nickel ball test, and it is greatly affected by the temperature of the water. So as we go to higher temperature water, the vapor jacket is much more tenacious and it lasts until a lower temperature. So it can be tempting to use higher temperature in water to slow down the quench, but we really don't want vapor jacket because that leads to inconsistent hardening. However, oil is much less sensitive to temperature variation. It will still form a similar vapor jacket, which will be eliminated at a similar temperature, even if we use higher temperature or lower temperature quenching oil. All right, let's move on to steel. I'm not an oil engineer, I'm a steel engineer, so I have a lot more to say about steel. Steel comes in different levels of hardenability, which is not how hard the steel can get, but that's how slow you can cool the steel and still reach maximum hardness. There are a few different tests of hardenability. One common one is the Jomini test. With the Jomini test, they take a bar of steel and they heat it up in a furnace. Then they place it in an apparatus where it's sprayed with water on one end. And so where it's sprayed with water is as fast as a water quench, and then it becomes progressively slower as it gets towards the other end of the bar, which is essentially air-cooled. So a very high hardenability steel will still fully harden throughout the entire bar. And then they grind one side of the bar so that they can measure hardness in 16th inch increments. And then we can see the hardness distribution across the bar with different cooling rates. So then if we compare Jomini curves for a few different steels, just to see good examples, you can see an air hardening steel A2 is just a flat line. It hardened fully throughout the bar. On the other end is 1095, a water hardening steel, where it only fully hardened at the very end of the bar and then quickly drops off to low hardness. In between, we have steels like 5160 and O1, which are basically oil hardening steels. O in O1 stands for oil hardening. And then 52100 is sort of in between oil hardening and water hardening. When we have steel annealed from the factory, it is in a very soft condition, so it's easy for machining. This soft condition is ferrite plus iron carbide. So the iron carbides are the hard particles that hold most of our carbon in this state. The ferrite is a soft phase of steel, which is the same as room temperature iron. When we heat up steel hot, it becomes non-magnetic. It transforms from ferrite to austenite. Austenite is the high temperature non-magnetic phase of steel, and it can hold a lot more carbon than ferrite can. And so we dissolve some carbide at this high temperature and put carbon in solution. And if we heat up even higher temperature, we dissolve more carbide and get more carbon in solution, which gives us more potential for hardness. When we rapidly quench the steel, we lock in the carbon and make this distorted structure called martensite, which is very high in hardness. However, if we slow cool, it allows the carbon to come out. It comes out as this phase called pearlite, which is a combination of ferrite and carbide, just like our annealed steel. But it forms in this unique structure because it wants to form both at the same time as we slow cool. And the pearlite is soft and undesirable if we want a nice hard knife blade. With a simple iron carbon steel, all that needs to happen is for carbon to diffuse over a short distance so that it can form the iron carbide and get the carbon out of the growing ferrite, which has almost no carbon in it. However, different alloying additions are also preferentially found in the carbide rather than in the ferrite. So if we add certain elements like manganese, chromium, molybdenum, then that will slow down the formation of the pearlite, and therefore these higher alloy steels can be quenched more slowly and still have full martensite for maximum hardness. Here are the compositions of the steels that I use to study the effect of different quenching oils. In approximate order of hardenability, or at least where we would expect them to rank. At the top are the water hardening steels like W2, 1095, 26C3 that have low manganese or low manganese plus a small chromium addition. Then we have steels that are more in the middle like 1084 with 0.74 manganese, or 80CrV2 with manganese plus chrome, or 15 and 20 with manganese plus nickel. And then we have our higher hardenability steels like 52100 with high chromium, or Crewforge V with a combination of manganese and chromium, or O1, which is quite high in manganese along with a chromium addition. On this chart, I have the exact composition where available for the bar of steel that I purchased, and if not, I have the approximate composition of each steel. So I bought all of these steels in 1/4 inch thickness, which is on the thick side for a knife, but that means that anything at that thickness will harden all the way through, and anything thinner will as well, obviously. Cross-section is very important in hardening, as something very thin will harden more quickly. So I took all of these steels, I measured them, and I cut them so that they're 1.5 inches wide and 2 inches long. I austenitized them at pretty generic temperatures for each steel. Then I quenched them in the oil, heated to between 120 and 150 degrees Fahrenheit. And then I ground away a 32nd of an inch to remove any decarb and measure the hardness, and then another 32nd of an inch and measured again, and so on until I reached the center, which was an 1/8 inch for the 1/4 inch material. And then I can measure both the performance of each oil with every steel and see how different steels compare to each other in terms of hardenability. Now, there can be some differences between different manufacturers because the structure may be coarser or finer as we receive it, and a coarser structure will actually have higher hardenability. Okay, so we're going to start with 1084. It ended up being in a very good place for comparing the oils, where it would fully harden in water and mostly with Parks 50, but once we got to slower oils, it was really showing the difference in speed between the different oils. So for water, of course, it hardens all the way through. With Parks 50, it hardened most of the way through until we were at the very center of the piece. And then as we go to Parks AAA, which is a little bit slower than Parks 50, it only got up to about 62 Rockwell at the surface. But it was still at 60 Rockwell at the center point, which is respectable. In terms of quench all and quench fast, they had a little bit of an odd behavior. The quench fast is supposed to be an 11-second oil, and the Quenchal 521 a 16-second oil. However, the quench fast started out harder, and then by the center, it was at a lower hardness than the Quenchal 521. So I'm not exactly sure what different factors are at play to end up with that result. The Quenchal, the 28-second oil, was very slow as expected. And then where does the canola end up? Well, unfortunately, the canola ended up at the very bottom of the chart. It ends up that canola is a very slow oil. So even though it doesn't really have vapor jacket issues, it doesn't form much of a vapor jacket, since it starts slowing its cooling rate right where it's important for the steel to avoid the perlite formation, it ends up acting as a very slow oil. When it comes to a very high hardenability steel like 01, then both Parks 50 and Canola look pretty similar. Canola is a little bit softer with 01, probably because of a phenomena called auto-tempering. With auto-tempering, as it cools slowly through the martensite transformation, it tempers over that short period of time, and so it ends up a little bit softer, even though it should be full martensite. With the water hardening steels W2, 1095, 26C3, they didn't fully harden even with Parks 50, but when I tried them with water, they did fully harden. Unfortunately, I didn't get the 26C3 in time to do the water hardening experiment on it, but this does show the quench rate difference between water and Parks 50. It can be pretty significant. I have heard some knife makers say that Parks 50 and water are basically equivalent or close to equivalent, but it is not the case. To look at the effect of cross-section, I also analyzed the water hardening steels after quenching from 1/8 inch stock as opposed to 1/4 inch stock. The 26C3, 1095, and W2 all failed to harden at 1/8 inch in canola. However, 1084 did come closer to hardening at least, though still not there. I also tried AAA, which again is a medium fast oil. The 1095 and W2, 1084, they all fully harden at that quench speed, but the 26C3 was a little bit softer than it is when it's quenched in Parks 50. But if we look at 26C3 at 1/8 inch, you can see that with Parks 50, it fully hardens very easily. So if you're using a water hardening steel, I would not recommend quenching anything beyond 1/8 inch really, unless you're going to attempt to do water. And at 1/8 inch, you really need as fast of an oil as you can get. So if we go up in increasing degrees of hardenability beyond 1084 versus 15 and 20, with Parks 50 and Quench Fast, which are fast and medium oils, it seemed to harden fine. With canola, it definitely was not fast enough where it was not fully hardening, at least at 1/4 inch stock. If we go up another step to 80 CRV2, this steel was hardening somewhat inconsistently. I saw something similar with 52100. Perhaps if we refine the carbide structure, that it would harden a little more consistently, though the hardenability may be somewhat reduced in that case. Regardless, the slow oils Quenching and Canola did not fully harden the 80 CRV2, which makes sense given that it is a borderline water, oil, fast oil steel. With 52100, again, we saw something sort of similar to 80 CRV2 with inconsistent hardening. The Canola and Quenching are maybe not fully hardening it, though at near the surface we saw Parks AAA and Quenching 521 also show a little bit lower hardness. With Crewforge V, it's fully hardened throughout regardless of the oil, so it's closer to 01 being a good medium oil steel. Okay, let's move on to commonly asked questions about quenching oils. One common concern is about quenching in an oil that is too fast. People are often asking between Parks 50 and Parks AAA because those oils are very common. And frequently knife makers will say, oh, this steel can't be quenched in Parks 50 because this steel is too hardenable and Parks 50 is too fast, so you need to use Parks AAA instead. The first thing to remember is that Parks 50 and Parks AAA are not that different from each other. Yes, Parks AAA is a little bit slower, but these are not vastly different oils. It's not like one is way, way faster than the other. They're in basically the same category of fast oils. But to alleviate your fears, I will bring up an experiment that we did with 8670, which is a relatively high hardenability steel in the same range as Crewforge V. When we quenched it in Parks AAA, it had good toughness, and when we quenched it in Parks 50, it had slightly higher toughness, probably just due to experimental scatter. Things that people worry about are so-called microcracks in the steel, and microcracks are a real thing, but they are not the result of quenching too rapidly. They happen from having too much carbon in solution. The rate you quench is not going to affect that. It's all about your austenitizing temperature. It dictates how much carbide you dissolve and how much carbon is in solution. Instead, what we worry about with quenching too rapidly is warping and cracking. Warping can be corrected. Cracking is a bigger problem. You'll know if it cracked. These are different than microcracks. But warping doesn't mean that you ruined the knife, and sometimes warping just happens anyway, even with an appropriate quenchant. The benefit to high hardenability steels is you can use slower oils and still fully harden to reduce your chances of warping and cracking, but it doesn't mean that you can't use faster oils, or even water if you're very careful. So which oil for which steel? That question is a little bit hard to answer because it depends on the cross-section and the manufacturer. Here I have a chart ranking steels by hardenability, with the steels at the very top being very low in hardenability and steels at the bottom being high in hardenability. Some of the tests that I did for this video ended up a little bit different than on the chart, which is probably due to differences in the structure as it comes from the manufacturer. As in all of these cases, 1095 W226C3, there are reported hardenability tests on these steels, which confirm the ranking. But regardless, with the steels that I have in the water hardening category, those are the ones that you really need to be careful with. Using water, anything above 1/8 inch, and at 1/8 inch and below, you probably need a pretty fast oil. So something like Parks 50 or Hotto Quench K would be best for these steels. As you go up, since knives are 1/4 inch or below, a lot of oils will work for a lot of these. I still don't recommend canola for any of them, but you can use a lot of oils as long as the cross-section is reasonable. But as I stated earlier, we don't really need to worry about quenching too fast in most cases, as long as we're not getting bad warps or cracks in our blades. If you're going to buy one oil, it should be a fast oil, since that's the most versatile. You can use it on a wide range of steels, even the high hardenability ones, but a slow oil you cannot necessarily use on the low hardenability steels. So the best way to do it is to have a fast oil and a medium oil. The medium oil to reduce your chances of warping and cracking with the higher hardenability steels. In the US, it's pretty easy to buy Parks 50 from Du Bois through their website. It's a little bit more expensive than the AAA. If you're going to be cheap, then get Parks AAA if you're in the US. Do not use canola.
All right, this study was pretty fun. I learned quite a bit, more than I thought I would learn by just
quenching a bunch of different steels into different oils. So some of the surprises were that canola was quite a bit slower than I thought it would be. It's a pretty common oil for beginners to use, and the fact that you couldn't even harden 1/8 inch 1084 in canola was quite a surprise. So I do not recommend canola in general. Other surprises were that once we got past about 1084 and hardenability, the higher hardenability steels were really quite insensitive to the choice of oil when it came to the final hardness and making sure that we get full martensite throughout. Thanks to my Patreon supporters, because without them I wouldn't be able to buy all of this oil and these steels to do these kind of studies and to answer questions a lot of knife makers have about how to quench their knives and in what oils. If you want to learn more about heat treating, you can go to knifesteelnerds.com. There's a lot of articles on there, or you can buy my book, Knife Engineering, where it has a little bit better progression than just reading articles on Knife Steel Nerds. So thanks everybody for watching.